being ultra-finitists on this channel. I claim I do not understand a proof if I can't get it done in one sitting. So we're going to restart. Just going to restart, and that's the accounting I give. Left off, we got one of the directions of the biconditional. We did not get the other direction. Alright, so Theorem 32. Is the assertion that R pipe A minus B is equal to R pipe A minus R pipe B. What is the pipe operator? No idea. Don't care. Okay. Which was the direction we could get? Looks like we were able to solve right-hand side to left-hand side. So let's start there. Or, well, okay, there's the proof, yeah, well. I guess we'll forego the ultrafinitism for today and just try to go in the other direction. Okay. let's do it. Okay. Alright, and we can do, if and only if D is an element of F. D is an element of R pipe A, not D is an element of R pipe B. Okay. So this is our end expression. If we cycle this negation through, oh, and then what we want is, let me think here. Well, if we cycle this negation through, we get for all C and for all D, not D equals the ordered pair CD, or not the ordered pair CD is an element of R, or not C is an element of A. We could extract a negation from this whole thing and get a conditional expression. We only need forward derivability. We don't need backward derivability, so there are some options that opens up. I don't know what we would get out of a negated conditional expression. We'd have to be able to redistribute the negation, in which case, not clear. Alright, let's distribute this negation through. Okay, so this closes this quantifier because we're going to change this to a for, these to for all. Okay, so D equals the ordered pair B. And the ordered pair B is element R. Incorrect, I already had that. Okay. So we can downstep this universal quantification and get back A and B if we want that for syntax. I actually don't know if I don't have a strong enough grounding in quantificational logic, sentential quantificational logic, whatever, to know whether we need to do that or not. I've kind of been winging it a little bit, and it's worked out up to this point, so far as I can tell. But okay, yeah, we can step this down. This should be B, not A. Similarly. So this will also close this quantification. Universal elimination. So we're going to get this expression. But I don't know how we're going to get that. This should be an or. Wait, don't I know how we're going to get that? Well, so we're going to end up using the same trick we used here. I don't see why that doesn't work. Let's see here. Yeah, I might have just been out of it last time. So we're going to distribute this and sequence. So the same trick that we performed in the last, or in the other direction, up here. So I guess we ended up repeating the first half of the proof effectively anyway. Why did that? That struck me. We looked at this. I don't know why I thought we couldn't do this in the forward direction. And so the idea here is that when we distribute this through these two expressions, d equals the order pair AB and not d equals the order pair AB, is a contradiction. The order pair AB is an element of R and not the order pair AB is an element of R is a contradiction. And then the last expression, A is an element of A and not A is an element of B, is not a contradiction, conveniently. So contradiction. Right, well the question is how do we arrive at this point and go in the other direction? But that isn't really a problem, right? Because I can OR on a contradiction if I want. So I just OR on these two contradictions and then we go in the other direction. Yeah, but we can't do that because this is forward derivable. If this were biconditional all the way back up to the beginning, that wouldn't be a problem, but right, so like this expression is D equals the order pair AB, and the order pair AB is an element of R, and A is an element of A, and not A is an element of B, which is what we can get up to from the left-hand side of this equality. Okay, and I can OR on these two contradictions to get back to this, and then re-extract. So it's reversible up to this point, but then we can't take the next step back. But actually, does that matter? Maybe that doesn't matter, actually. so let's go back to the left to right calculation. So we can forward derive here, and or on these terms. So we're back here, and then we can anti-distribute. I suppose we'll write that out, so that's the same as there exists an A and there exists a B. Thunder. So first thunder of the season. D equals the ordered pair. AB. And the ordered pair AB is an element of R. And A is an element of A. Okay. So this is all under one quantification. Not D equals the ordered pair AB. Or rather, that becomes significant. Because we're going to be extracting the negation, flipping all of the ors. So the point ends up being that we don't need the separate quantifiers, seemingly. The reason I would think this proof isn't going to work is because we have quantifiers for A and B, whereas on the way forward we had additional quantifiers for C and D, but I guess I'm thinking we might not need those additional quantifiers. And we don't have a chance to introduce those quantifiers, so I'm thinking. Okay, but then why can't we Yeah, I don't know. I'm still really loose on quantification. Like, if these were individuals, or if these were named, if these were constants, then I could do existential introduction. For that matter, I could say if there exists an A and there exists a B such that D equals the order pair AB, just as an example, then I could say if and only if there exists a C and there exists a D such that D equals the order pair CD. And then I might want to and A equals B and and A equals C and B equals D, but I don't think I would have to do that. Alright, now what are we going to do? Right, well now we're extracting the negation. Okay, so... which is interderivable with the much shorter expression. D is an element of our pipe A, and not D is an element of our pipe B. If and only if. Alright, well that's it. I thought this was gonna require more time, but apparently not. Though we also started in the middle of it, so maybe that's not a good debut for naming. And stream title. After the theorem that we're doing. Alright, there you go. Now, what are we gonna do? Is that difficult to read? Is that lighting a little bit harsh? Maybe I need to harsh it now. Yeah, probably not. Let's see. Harshen the lighting even more. Increase the zoom a little bit. Still want the colored pencils in frame though. Alright, now Theorem 33. Okay. R/S bar A, pipe A rather, is equal to our pipe A/S. Now, I still don't know what the pipe operator actually does. Well, I don't know, that's a philosophical question. The pipe operator is whatever makes me do proofs like this. So do I know what the pipe operator is? I don't know what its name is. I don't know the context in which one would use it. I don't have a good idea of what sense I would want to draw or write out if I were working in a set theory with individuals. or if I spent any time thinking about sets as if they could be. I don't know what sets I would draw if I wanted to construct finite sets that instantiated these properties. But do I need to in order to know what the operator means? I don't know. Anyway, I do have to recall what the slash operator means. For all D, I might have warped my quantification a little bit in the last proof. I don't know. For all D is an element of R slash S pipe A if and only if. Well, we don't have to know yet. We can do the next step. There exists an A and there exists a B such that D is equal to the ordered pair AB, and the ordered pair AB is an element of R slash S. That should be bracketed. And A is an element of A. Okay. R slash S. That's, there exists a C such that the ordered pair AC is an element of R and the ordered pair CB is an element of S. Okay. If and only if D is equal to the ordered pair AB and there exists a C. Such that the ordered pair AC is an element of R and the ordered pair B, nope, CB rather, is an element of S. And A is an element of A. Okay. Alright, well, let's call that the forward direction. What does it look like from the other direction? For all D, rather, let's say for all E. E is an element of exists a D, and there exists an E such that D is equal to the ordered pair DE, where E is equal to the ordered pair DE. And there exists an F such that the ordered pair DF is an element of our pipe A, and the ordered pair FE is an element of S. Yeah, maybe we would prefer to have a continuation of the colors. Or, well, this keeps it order based, but alright, order based only. Anyway. Now what do we want to do? Well, we have another simplification step. The ordered pair DF is an element of our pipe A, which tells me that the ordered pair DF is an element of R and D is an element of A. Okay, probably should have just gone to the next page rather than going into the gutter, but whatever. Alright, well we have a term here, D is an element of A is an element of A. And conveniently, E, the ordered pair DE, has as its first coordinate, first element D. Here, D has its first coordinate A, element A, whatever. Okay, so D corresponding to A makes good sense. And now we have the split term here. So if we merely pattern match all A's for D's, we get if we pattern match A's for D's, B's for E's, and C's for F's, we get the same expression. The question is, how do we justify that step? Or, relatedly, do we need to justify such a step? No, actually. We should just be able to rearrange, I'm thinking, and then follow back through. Okay. It should be D. So, this feels a little bit disheveled. Oh well. Another proof down. Interderivable the entire way. The next definition introduces the notation R double quote A, which follows that of Whitehead and Russell. Okay. The next definition introduces the notation R double quote A, which is read the image of the set A under R. Thus, if R and A are defined as in the previous example, where's the yeah, okay, we're just going to work with the definition. Okay. So, definition 9. R double quote A is equal to the range of R pipe A. Okay. Well, and that conveniently gives us, the definition gives us that easily, I would say. What do I mean? Because R pipe A, if an ordered pair is an element of R pipe A, that gives us that the ordered pair is an element of R, and the first element of the ordered pair is an element of A. So if we're taking, oh, well actually this is giving us the second element range, right? Not the domain. Alright, so well, I guess the pipe operator already selects its first element, and now we have a way to select its second element. Okay. So, for all, and this will be a lowercase letter, I'll do S for all S. S is an element of R double quote A. This is another one that requires a parenthesis for the set we're talking about. Okay, this is an element of R double quote A is interderivable. Actually, in this case, is defined. I have to think about. Range is, there exists a D exists a D and there exists a T such that D is equal to the ordered pair TS, and probably we don't need that term. The ordered pair TS is an element of R pipe A. Okay, that should be a bracket. Varied if and only if interderivable with D is equal to the order pair TS and the ordered pair TS is an element of R and T is an element of A. Okay, which to rewrite for all S is an element of R double quote A is assigned to there exists a D and there exists a T such that D is equal to the ordered pair TS and the ordered pair TS is an element of R and T is an element of A. Okay. It's a lot of space to leave blank at the bottom of the page, but I've got additional notebooks. Alright, so we'll have Theorem 34. Okay, which says that most of the proofs of the theorems concerning images of sets are omitted. To reduce the number of parentheses in the statement of these theorems, we use the convention that union, intersection, minus dominate double quote. Okay, so thus R double quote A union B is R double quote A union B, not R double quote A union B. Okay, I don't know what dominate is supposed to mean in that context, but okay. Well, no, I can figure it out. I don't know why you would choose that word, rather. Anyway, so this doesn't have a quantifier. This says merely y is an element of R double quote A. I'm going to put in the quantifier. I'm going to say for all S. For all S, is an element of R double quote A, is interderivable with the expression there exists a T such that the ordered pair TS is an element. Yeah, the author kind of. Okay, we'll do T. T is an element of R double quote A is interderivable with the expression that there exists an S such that the ordered pair ST is an element of R and S is an element of A. And that seems like merely a restatement of the definition. Let's see. T is an element of R double quote A is defined to be equal to defined to be interderivable with oh, well, yeah, yes, we just proved this theorem by working out by decomposing the definition. So there exists a D and there exists an S such that D is equal to the ordered pair ST and the ordered pair ST is an element of R and T is an element of A. Yeah, we've given ourselves the ability to remove these expressions without stepping down by conditionals, as you would normally do when dropping an AND. Wait a minute. This should be yes. So expression that D is equal to the ordered pair ST is more record keeping. Let's rid ourselves of this confusion. Yeah, we have the space to rewrite it. Let's just rewrite it. Alright, so for all t is an element of R double quote A is defined as equal to, there exists a D and there exists an S such that D is equal to the ordered pair ST, and the ordered pair ST is an element of R, and S is an element of A. Sure. Okay. Theorem 35. Okay, R double quote A union B is equal to, right, unlike the author, I have no qualms about stacking parentheses, so R double quote A union R double quote B. Right. For all D, D is an element of R double quote A union B is interderivable with the expression that there exists an S and there exists a T. No, yeah, this should be T. This is not a set. No, it doesn't have to be a set. For all T, T is an element of R double quote A union B is interderivable with the expression there exists a D and there exists an S. Such that D is equal to the ordered pair ST and the ordered pair ST is an element of R and S is an element of A union B. I'll go ahead and simplify or, extract this term. S is an element of A, or S is an element of B. Okay. Alright, so this is merely a question of distribution. Take this to be our term to distribute. Distribute through here, we distribute through here. This is interderivable with the expression think this D equals. In most of these proofs, we can probably just eliminate that. And maybe all of them. The order pair is T is an element of R, and S is an element of B. Okay. If and only if. Probably only needed one of these color signals. Let's see. If and only if T is an element of so this would close out the S quantification. The D and S quantifications. Okay. Or T is an element of R double quote B. Okay, if and only if interderivable with T is an element of R double quote A union R double quote B. And that is a proof. Theorem 36. R double quote A intersection B is a subset of R double quote A intersection R double quote B. Alright, so the puzzle here will be, why do we have to step down the biconditional? Where do we have to step down the biconditional? Alright, yeah, okay. Do this. Alright, so for all T, once again, T is an element of R double quote A intersection B is interderivable with the expression. There exists a D, and there exists an S. Such that D is, yeah, let's just get rid of that. I don't think we're gonna need that. Okay. A strange use of goldenrod, but I like it. Alright, so we're going to skip that. We're going to say the ordered pair ST is an element of R, and S is an element of A, and S is an element of B. Alright, well, we haven't had to step down the biconditional yet. It's usually more obvious why you have to step down the biconditional when you go in the other direction. Let's duplicate this term, which does not step down the interderivability according to our rules anyway. The ordered pair ST is an element of R, and S is an element of A. And the ordered pair ST is an element of R, and S is an element of B. Yeah, well, I mean, you can always show they're equal and then establish the fact that one is a subset from the other. One is a subset of the other from the fact that they're equal to each other. But that is generally not the point in these theorem statements. So it ends up being a quantifier problem, but that still doesn't tell me why I have to step down. So if you try to go in the other direction, you don't get that. You don't get only S, is the point. So that should tell me something about where to step down the biconditional, the interderivability assertion, but I don't know where. I guess it is here, yeah. No, it wouldn't be. Yeah, because actually we close the quantification on S in this step as well. So actually, that's going to be a regularity. I'm thinking that closing a quantification is going to proceed often going to proceed a step down, or rather, when we have a step down, we're going to have a closing of a quantification. Then T is an element of R double quote A, and T is an element of R double quote B. How did there end up being so much space between these two lines? And to illustrate the point, let's try to go in the other direction. Yellow means something like conjecture I expect to be false. For all T is an element of R double quote A intersection R double quote B is interderivable with the expression T is an element of R double quote A and T is an element of R double quote B, which is interderivable with the expression there exists an R such there exists an R such that the ordered pair, no, that should be single bracket, I think. The ordered pair RT is an element of R and what is this? What is the definition? And R is an element of A, and there exists an S such that the ordered pair ST is an element of R, and S is an element of A. Okay. And that's where we can't continue the derivation. step down or without step down produces a system error. That should be B. There exists a Q such that the ordered pair QT is an element of R and Q is an element of A. And the ordered pair QT is an element of R and Q is an element of E. System error. Alright. These proofs were just a little bit longer, I wouldn't have to feel guilty about leaving so much blank space at the bottom. A simple example shows that inclusion cannot be strengthened to identity in this theorem. No, it doesn't. A simple example shows that inclusion should not be able to be strengthened to identity, I suppose. This is not quite the same point. We can do some scratch work. Or we could just start it here and not have every theorem start at the top of the page. That works just as well. Actually, this only took this long. It's possible that we could prove this on this page. Give it a shot. Theorem 37. Though this is interestingly different from the preceding proof. This has the the double term in front as the antecedent, and the single term as the consequent. Interesting. Did I write that down wrong? No. Alright. Did the author write it down wrong? Maybe. Let's see. So we need there exists an R and there exists an S again. Well, there exists an R such that the ordered pair RT is an element of R, and R is an element of A, and there exists and not. Ah, I see, that's interesting. And not there exists an S. Put that negation outside of the bracket. Not there exists an S such that the ordered pair ST is an element of R and S is an element of B. Okay. Which is interderivable with the expression the ordered pair RT is an element of R and R is an element of A, and I guess technically we should have here, and also this will close out the Spanish orange quantification because we're distributing this through, so this is now going to say for all S, not the ordered pair ST is an element of R, or not S is an element of B. Which will get true green quantification. Okay. These colored pencils just keep going. My colored pencil collection feels basically undiminished. I haven't run out of any of them over about a year and a half. Admittedly, I'm not filling up pages with color, but anyway, so now I think the point is that we want to step this down. And this is also where we get the subset from. So this is now going to be, we'll also close out that quantification. The ordered pair RT is an element of R, and R is an element of A. And not the ordered pair RT is an element of R, or not R is an element of B. this is a matter of distribution. Where, as with an earlier proof, these two terms become a contradiction. So this color and here. Yeah, ideally these would be the same. Okay. There's a contradiction. Whereas this is not a contradiction. Which is interderivable with the ordered pair RT is an element of R, and R is an element of A minus B, which is interderivable with the expression that T is an element of R double quote A minus B, which is that which was required to be demonstrated. And we did it all on the same page, look at that. Okay, the author makes note of that. Let's see. Oh yeah, so yep, so he uses the same idea. So we get confirmation that this approach is valid according to Suppes' technique, at least. Here we have for all z are y, then not z is an element of b. And here we get the replacement of z with x. Then the author makes the curious decision of keeping the step down. I think that is an artifact of the fact that once you've stepped down a biconditional, you can't get it back. Like, I don't think you have to keep stepping down the conditional expression here. We maintain that distinction, so here I use the biconditional, the interderivability assertion. Rather than the forward derivability assertion. Well, I mean, if I started here, if for whatever reason I started my proof in this step, I could say this line, if and only if this expression, which is a downside to always stepping down. Though, if it's more expensive to, like if you were, again, this is speculative, but if you were working with a system where it was more expensive to maintain an interderivability assertion, then once you have to step down once, you might as well just keep stepping down every step. is a subset of B. Is forward derivable with the expression. R quote A is a subset of R quote B. Okay. What time is it? Okay. Well, naturally, we will start with the left-hand side here. For all t, if t is an element of A, then t is an element of B. Okay, that's about as far as I've gotten so far. Let's look at the other end. For all u, yeah, we could do blue, or we could stick with red. Yeah, okay, we'll stick with red. All right, so for all u, u is an element of R double quote A. U is an element of R double. This bracket was fine. Yeah. Okay. Then U is an element of R double quote E. Okay. Which is interderivable with the expression. Let's see. Yeah, okay. Not U is an element of R double quote A, or U is an element of R double quote B. Which is interderivable with not there exists I guess PQ. Sure. Not there exists a P such that let's see, I might have to take a break shortly. Not there exists a P such that the ordered pair PU is an element of R is an element of A, or yeah, negation introduced this strange bracketing. Whatever. Or there exists a Q such that the ordered pair Q U is an element of R, and Q is an element of B. Alright, which as before, as in one of the earlier proofs we did today, it's going to step down. And we're gonna, oh, never mind, oops. First we need to distribute the negation. Interderivable with, for all P, not the ordered pair Pu is an element of R, or not P is an element of A, or, so that would also close out orange. And then I guess we would open up green. Not the ordered pair P is an element of R, or not P is an element of A, or the ordered pair Q U is an element of R, and Q is an element of B. Okay, now I will step down the conditional, the derivability assertion, and say, and then I'll also close out quantification on P. Not the ordered pair Q U is an element of R, or not Q is an element of A, or the ordered pair Q U is an element of R, and Q is an element of B. So same idea as earlier. We're going to distribute through with this as the P, this as the Q, and this is the R. Wait a minute. That's not going to work. No. We got this or, it's not an and, we got this or from the conditional equivalence. Alright, let's call this an error and distribute it in the other direction. Well, we could do it in both directions and see what's more useful. Okay, then we'll say, confusingly, this is actually, it makes more sense to do that. Yeah, okay, let me just... Okay. That's confusing notation, but whatever. Okay. Okay, we'll do, okay. Breaking out rules, organization rules we haven't used in a while. Alright, so this will be case A. And that's going to give us yeah, okay. Not the ordered pair Q, U is an element of R. Or the ordered pair Q, U is an element of R and Q is an element of B. Or alright, this rule. Okay, and then not Q. Getting confused here. Q is an element of A. I'm not sure I like that notation. The idea is to give it a colored hat to say that this is after the distribution. This is what had this color prior to the distribution, but it just looks like maybe looks like I'm underlining what's above instead of capping what's below. Anyway, or Alright, which is interderivable with the expression not the ordered pair Q, U is an element of R, or the ordered pair Q, U is an element of R, and not the ordered pair Q, U is an element of R, or Q is an element of B. Or not Q is an element of A, or the ordered pair Q, U is an element of R, and I'll go ahead and line it up at the and. This is a tautology. Yeah, I don't know what we're getting out of this. Well, that's why we're doing it both ways. Okay. So now if we distribute in the other direction, we get let's see. Not the ordered pair Q, U is an element of R. Or not Q is an element of A, or the ordered pair Q, U is an element of R, which is a tautology. Let's see. And yeah, we'll just underline the thing. Alright, so that's tautology, leaving the truth of this expression up to the other term. Which is not a tautology, though it is simpler. Now, what do I want to do with this? There's a problem here, right? The problem is that we've stepped down on the right-hand side. So while all of this might be interesting in its own right, it's outside the scope of what we're trying to prove. Though to finish it out, I think I see how we finish this out. This is interderivable with the expression not the ordered pair Q, U is an element of R, and Q is an element of A, or Q is an element of B, which is interderivable with the expression that if the ordered pair pair Q U is an element of R, and Q is an element of A, then Q is an element of B, which is interderivable with the expression the order pair Q U is an element of R, and Q is an element of A, then the ordered pair Q U is an element of R, and Q is an element of A, and Q is an element of B. Okay, which is forward derivable. No, wait a minute. Yeah, which is forward derivable. But again, that's a problem. We don't want to be forward deriving the right-hand side of this. But okay, forward derivable with which is interderivable with the expression U is an element of, could have simplified this a little bit earlier, but U is an element of R double quote A, then U is an element of R double quote B. Which is ostensibly what we're looking to interderivable with the expression R double quote A is a subset of R double quote B. However, oh, well, that should be unsurprising because that's the expression we started with. So it's convenient, I mean, it's reassuring that we got back the expression we started with. It's better than if we could not get back the expression we started with. I'll take a break here. I'll be right back. we have independently proved P than P. What journal will we submit this proof to? So, yeah, if we go back to oh, that's the wrong color. Alright, so for all t, t is an element of A, then t is an element of B. Taking the conditional equivalence, this is interderivable with not t is an element of A, or t is an element of B. Okay, and it looks like we want to get to this expression, or this expression. Let me get my scratch notebook here. Which is more impressive when I pull it out and it's also filled with text, but I'll have to refill it. So I think what we're doing here is ending on a tautology. So we have we're starting with for all t, t is an not, rather t is an element of A, or t is an element of B. Okay. If and only if quantification is a little bit out of position, but it doesn't really make a difference. Not T is an element of A, or T is an element of B. And it's not clear what whether I want to and on a tautology or on a contradiction here. Let's see. Actually, yeah, let's call this. Well, this is the scratch notebook anyway. It doesn't really matter. Okay. And there exists an S such that the ordered pair ST is an element of R, and S is an element of A. Or not. Nah, yeah, that quantification doesn't make sense. Yeah, but we can do not there exists. Yeah, okay. Not there exists an S such that the ordered pair ST is an element of R and S is an element of A. Okay. This distribution is a little bit horrible, but doesn't do the job. What exactly do I want out of this? I could do some horrible logic here. Okay, so this is P or Q. And R and S, or not T. So we could immediately step down this universal quantifier, and then actually we could distribute this first expression through the second expression, which might simplify in our favor. And we're not using this. We don't need to negate here. We'll just sub in. We'll include the negation in subbing in. Or U. Okay. So this would be interderivable with P or Q and T or U or R and T or U or S. From which we could derive this sort of undirected logic, which is, if it works, is only conveniently so. Let's labels. This is P, Q, R, S, T, and U. So the expression that gets S and U is going to be a tautology. Either S or U. So then we're going to have neither of these two distributions are convenient. Okay, P and T. I'll put this in alphabetical order, I guess. R, T, U. Or Q. And R or T or U. Okay. Switching back and forth between print and cursive R. Okay. Now P and R would be the expression not T is an element of A, and the ordered pair ST is an element of R, which doesn't seem useful. And then P and T, not T is an element of A, and not the ordered pair ST is an element of R, which also does not seem useful. And then with the U expression, we could step that down to saying T, and then we would have not T is an element of A or not T is an element of A, which is also not useful. And then oh, I think I see the point. Maybe. No, I don't. Okay. Alright, that doesn't seem to be going anywhere. Let's go back. Wait, can I? Yeah, we could just be doing. Maybe the point is just to do not to or on a tautology, but just do or introduction. We can always or introduce. We can and on we can and on a tautology. You could also or on a contradiction, but you could also step down. Like you can establish interderivability with a term and a tautology, or you can step forward with an or introduction. So we could do not T is an element of A, or not there exists a P such that the ordered pair PT is an element of R and P is an element of A. Okay. So let's step down here. Well, yeah, we might want to do this in Scratch. Make sure this works first. It's forward derivable. Not T is an element of A, or not there exists a S, sure, not there exists an S such that the ordered pair ST is an element of R and S is an element of A. Okay, we'll say or T is an element of B. Alright, now this is interderivable with the expression not T is an element of A and there exists an S such that yeah, I don't know if we'd want to change the quantifier. I'm getting whatever. The ordered pair ST is an element of R and S is an element of A. Or T is an element of B. Okay, which is interderivable with the expression not T is an element of R double quote A, or T is an element of B, which is interderivable with T is an element of R double quote A, then T is an element of B. Right, now the question is, what wizardry do we need to pull off here to get T as an element of double quote to B? So sort of new goal Actually, yeah, we could have a simpler goal. T is an element of B, then is forward derivable with T is an element of R double quote B. Which I take back saying that yellow means it's unlikely to be correct. Okay, so can we forward derive here? Well, so I could say T is an element of B and there exists an S such that we're ending on a tautology at the moment. But that's going to give us an or that we can't get rid of. We could or on a contradiction, but then we can't get the term that we want. There exists an S such that the ordered pair ST is an element of R, and S is an element of B. But we don't need that term. Right, okay. Let's call that routing. So let's say T is an element of B or there exists an S such that the ordered pair ST is an element of R and not. There exists an S such that the ordered pair ST is an element of R. Okay. So this would be forward derivable, but that's fine. Oops. Okay. I'm losing it. I don't have a good way of indicating what I'm trying to indicate here, which is a bad sign. Alright, so forward derivable with T is an element of B, or there exists an S such that the ordered pair ST is an element of R, and okay, but once again we don't have to or on a contradiction. We could do this and then shed the and expression, but then why would you do that, right? So another rounding error. This is why we went to scratch. So, forward derivable with T is an element of B Okay, but the or doesn't work. It has to be and. Like, yes, we can or this term on, but it doesn't do us any good to do that. Also, this isn't the definition anyway. It's that S is an element of A or B. Right, we're getting that from here. No, hold on. Alright, well, I might be losing it a little bit early today. Let's go back to our definition. Where was that definition at? Oh, there. For all t is an element of R double quote A is defined as assigned. There exists an S such that the ordered pair ST is an element of R and S is an element of A. So indeed that is not where we're getting that term from. We have to introduce that term maybe I see. So if we go back to right, if we have T is an element of R double quote A, then T is an element of B. Let me once more confirm if I have P then Q. I think we're supposed to do these with capital letters. Okay. P then Q. Alright. If and only if not P or Q. Okay. Forward derivable with not P or Q and not P or P. Actually, that's interderivable because this is a tautology. which is in turn interderivable with the expression, so we extract this negation, so not P or P and Q, which is interderivable with the expression P then P and Q. Okay. Not P or Q and not P or P. Okay. So it is indeed interderivable. So this is T is an element of R double quote A, then T is an element of B, is interderivable with the expression yeah, I mean, we could go back up here and take the shorter routing. No, actually, we can't do that. Well, whatever. Well, so the original expression is let's see. T is an element of A. Yeah, I've gotten lost at some point along the way. We're gonna have to do the whole thing over with less confusion. And there exists an S such that the ordered pair ST is an element of R, and S is an element of A. Then T is an element of B. No, yeah, this doesn't get us where we're wanting to go. Because what we need is S as an element of B, as we just confirmed. As we confirm here. So we say for all T, T is an element of R double quote A, if and only if there exists an S such that the ordered pair ST is an element of R and S is an element of A. Okay, so this T is the second element, S is the first element, and it's the first element that we have as an element of A, or B in this case. So I mean, the idea was to say this is interderivable with the expression. Yeah, I guess we would drop this term, which is strange, because this is all we had from the original expression. Okay, so we can say T is an element of R double quote A, then T is an element of B, and there exists an S such that the ordered pair ST is an element of R, and S is an element of A. But if S is an element of A, then S is an element of B. Because we have that A is a subset of B. So this we can forward derive into the statement that S is an element of B. That got horrible. That got really bad. Let's see. So let's start over. Back over here. For all T is an element of A, then T is an element of B, which is interderivable with the expression not T is an element of A, or T is an element of B, which is forward derivable with the expression actually we could do the duplication now. My look ahead time has reduced to a handful of seconds. Is interderivable with T is an element of A, then T is an element of B, and if T is an element of A, then T is an element of B, which is interderivable with the expression not T is an element of A, or T is an element of B, and if T is an element of A, then T is an element of B. I think we'd want to keep this quantifier hanging around, though we keep the quantifier up front, so it might sort of come out of nowhere when we use this, but... Alright, so we'll store this in blue. Now, we could also just say this is a hypothesis, so we can and this on anytime we want. I guess it's a matter of style, I don't know. Alright, so this is interderivable with... nope, not interderivable, forward derivable. Forward derivable with not T is an element of A, or not there exists an S such that the ordered pair is T is an element of R and S is an element of A, or T is an element of B. Okay. And blue. Okay. And then we will say we group all of this is an element of A, and there exists an S such that the order pair ST is an element of R, and S is an element of A. Okay, or T is an element of B. And blue. Which is interderivable with the expression T is an element of A, and there exists an S. Yeah, okay. Sure. Such that the order pair ST is an element of R, and S is an element of A. Then T is an element of B. And blue, which is forward derivable with the expression I'll just keep that for now. So T is an element of A, and T is an element of R double quote A. Okay. Then this is stretching my logic capabilities a little bit. Then T is an element of B, and T is an element of A, and this term Now there's a question of when am I willing to and things down? Which curiously is a question we haven't had to ask much. Like, should I be willing to and down this? T is an element of A, and then similarly T is an element of A over here. And then furthermore, when we extract, let me think here. Okay, let's make note. So if I am willing to and that down, then also plausibly, well, if I'm willing to and that down, I could have anded it down before before passing the antecedent into the consequent. Also, this is interderivable, not forward derivable. And then the strange thing here is that we also want to and this down. Then there exists an S such that the order pair TS, rather ST, is an element of R, and S is an element of A. And for all T, yeah, okay, we could just say A is a subset of B, just to get a shortening. Okay, so now what is the idea? This will be not violet blue. Or there exists an S such that the order pair ST is an element of R and S is an element of A. And A is a subset of B. Okay, now if we distribute this through, so this will be P or Q and R, which is interderivable with P and R, or Q and R, which is forward derivable with this is so much trickery going on here. I don't know if I believe it. P and R. Yeah, maybe I'll spend some time making a Wittgensteinian point here towards the end. Oh, hold on. You're supposed to step that down. So we distribute and then we immediately step this down, which conveniently we can do because we were distributing an and. Conveniently, let's see. So now this is going to be not violet. Could have put the negation inside the color. Or there exists an S such that the ordered pair ST is an element of R and S is an element of A. And for all T, if T is an element of A, then T is an element of B. Maybe this should be a U. Alright, which we can then step down to saying not violet blue. Or there exists an S such that the ordered pair ST is an element of R and S is an element of A, and if S is an element of A, S is an element of B, which is interderivable with the expression not violet blue, or there exists an S such that the ordered pair ST is an element of R and S is an element of A, and S is an element of B, and if S is an element of A, then S is an element of B, which is forward derivable. We're going to AND this down. Not violet blue. Or there exists an S such that and we're also going to AND down S is an element of A. Okay. Interderivable with not T is an element of R double quote A, or T is an element of R double quote B, which is interderivable with if T is an element of R double quote A, then T is an element of R double quote B, which is interderivable with the expression that R double quote A is a subset of R double quote B. Horrible. Horrible, horrible, horrible. No good, very bad. Would you say that was surveyable and perspicuous? Imminently surveyable. It fits on a page, though. Alright, so this is going to get the routing error evaluation. And I'm going to restart this proof, because nothing I've done up to this point has actually made any progress. This was a big loop. This was a big loop. Alright, so Theorem 38. For anyone keeping score. A is a subset of B is forward derivable with the expression R double quote A is a subset of R double quote B. For all T, but you know, we didn't really settle this question. Should I be willing to derive, or rather, should I be willing to step down should I be willing to step down these AND expressions in, actually it was back here. I'm willing to do it in the consequent for sure, because if I'm saying P, then Q and R, okay, and P, this is interderivable with the expression P, then Q and R, and P, and Q and R. Okay, and now it's merely a question of anding down. Yeah, well, we can and down all of that, which gives us Q and R. And then we can and down the R. Well, we can and down whatever we want out of this and expression. Okay, now what's less clear is my willingness to and down. In the antecedent. And in fact, I think I'd say at first blush, I am not willing to and down in the antecedent. If I say P and Q, then R, we're not going to be able to derive R unless we have both P and Q. This is a restriction as opposed, it's like this is the payoff and we can drop as much of the payoff as we want, but this is a restriction. We only get R if we have both P and Q. And then as a mechanical instead of, as a syntactical instead of semantic observation, this turns into observing that we get not P and Q, or R if which is interderivable with, yeah, well, I can't say not P and Q, therefore not P. This would turn into not P or not Q or R. Okay, which makes this an error. This step down is an error, seemingly. I don't know what to do about that. Well, and we could note that if I say T is an element of A and T is an element of R double quote A, this is interderivable with the expression T is an element of A and there exists an R, or there exists an S, such that the ordered pair ST is an element of R and S is an element of A. Which is to observe that we can't derive the fact that T is an element of A from the statement that from the assertion that the ordered pair ST is an element of, rather, we can't derive the assertion that T is an element of A from T being an element of R double quote A. Well, we could carry the proof through to the end just to catalog this, so... For all T is an element of A, then T is an element of B, and A is a subset of B. Well, okay, yeah, we'll be precise here. Actually, then this is also a routing error. Well, okay. We'll just double up and then simplify. And then it won't technically have been a routing error, I guess. Okay. Or we could start over on a new page. Okay. Find Theorem 38. A is a subset of B. Is forward derivable with the expression R double quote A is a subset of R double quote B. Okay. So A is a subset of B, is interderivable with the expression A is a subset of B, and A is a subset of B, which I will immediately store in blue. Now, if I were really being resource intensive, we would adopt, or resource conserving of my pigmentive resources here. We would observe that we can always bring back in a premise, which is precisely because we could just carry the premise around. Well, so I think technically we can always and back on a premise because we could have anded it on at the beginning and carried it with us through the proof. But anyway, if and only if for all t if t is an element of A, then t is an element of B. And blue. And it's not just pigment, it's also time, because I have to pick up the pencil below. Alright. Which is interderivable with the expression. Not t is an element of A. Actually, so we could... Yeah, the conversion, taking the conditional equivalence is not really necessary, because we could give ourselves a syntax rule. As readily as we give ourselves any other syntax rule, we could observe that if I have P, then Q, interderivable with not P, oops. Not P or Q, which is forward derivable with the expression not P or Q or R, okay, which is interderivable with the expression I'll say not R. Okay, which is interderivable with the expression not P or not R or Q, which is interderivable with the expression not P P and Q, rather not P and R. Or Q, which is interderivable with the expression P and R, then Q. Okay, and what that tells me is that, so this is double crosshatch interderivability. If I have P, then Q, I can always forward derive P and R, then Q. Convenient lemma. Okay. What time is it? We're just about out of time. Yeah, I'm not going to have time to go through this whole thing. Not T is an element of A. Or T is an element of B. And yeah, I think we will. Let's do, okay, though, then, yeah, we can call that a routing error. Alright, so, if I have, we'll just repeat the proof I just did, P, then Q is forward derivable with the expression, interderivable with the expression, not P or Q, which is forward derivable with the expression, not P or not R or Q, which is interderivable with the expression, not P and R or Q. Which is interderivable with the expression P and R, then Q, which reveals that if we have P, then Q, we can forward derive P and R, then Q. Label this a lemma. Okay. So, interderivable with T is an element of A, and there exists an S such that the ordered pair ST is an element of R. And S is an element of A. blue. Actually, can get this done. And then I'll go ahead and make my short Wittgensteinian point. Okay, this is in turn interderivable with T is an element of A, and should I be willing to do shorter term lead definitions, I wonder. T is an element of A and diagram blue. Then T is an element of B and diagram blue. Okay, and true blue. Which is interderivable with the expression T is an element of A and T is an element of R double quote A. Okay. Then T is an element of B and there exists an S. Such that the ordered pair ST is an element of R and S is an element of A. And true blue. I will introduce another lemma here. See, this is like this. And this was correct. So this will be our way of introducing lemmas. Okay, this lemma is, let me see. I think we have to use specific terms for this. Well, no, not really, because if we're saying P, then Q, and R. Okay. This is forward derivable with P. I didn't need to double bracket that. P, then Q and R. Okay. So, start with being a little bit inconsistent about my bracketing. I'm in a rush. P, then Q and R interderivable with the expression not P or Q. derivable with the expression not P and R or Q and R, which is forward derivable when we end down R in the antecedent. We get not P or Q and R, which is interderivable with P then Q and R. Okay. Close out the lemma. So what we get here is forward derivability with T is an element of A and T is an element of R double quote A. Then T is an element of B and dark blue, diagram blue rather, and true blue. So let's store the antecedent in violet blue. So we have interderivable. Should be more consistent about where those symbols go. They usually get decided by where I have space. Anyway, violet blue. Then T is an element of B, and there exists an S such that the ordered pair ST is an element of R, and S is an element of A, and for all U, if U is an element of A, then U is an element of B. All right. So let's state another lemma. Actually, I kind of like having this to indicate the opening and closing. So we'll say this was, in fact, not an error. Okay. So now we will open up a lemma. Pencil sharpener go. Yeah. Here. So if I have P, then Q and R, this is forward derivable with P then Q. Okay, so how do we demonstrate that? P, then Q and R. Interderivable with the expression not P or Q and R. And down. This is more an expression of what I am willing to do as a calculative step. You'd think I would need to have solved something like this earlier, but actually no, this might be the hardest proof. Well, actually we haven't succeeded yet, so it could turn out to be that it's quite easy to prove this, and we just aren't finding the easy proof. But yes, this is the most logical work I've had to do for any of these proofs. Okay, so now we're going to say this is forward derivable, and we're going to and down T is an element of B. That's a little bit premature because we still have to work through this. So we'll say forward derivable with violet blue, then there exists an S such that the ordered pair ST is an element of R and S is an element of A. And yeah, we've kind of dropped quantification here as well. We'll have to go back through anyway. And if S is an element of A, then S is an element of B. Which is interderivable with, I guess maybe we want that convention on the left. Interderivable with violet blue, then all right, and then we will step down, removing this and removing this. Okay, which gives us violet blue, then there exists an S such that, I don't know why I put brackets there. Yeah, well, proliferation of brackets is not my concern. S is an element of B, and the order pairs T is an element of R. Okay. Which is interderivable with the expression. Let's mark these step downs. Interderivable with the expression that violet blue, then T is an element of R double quote B, which is interderivable with the expression T is an element of A and T is an element of R double quote A. Then T is an element of R double quote B, which is not what we were trying to prove. Which we can show by saying, let's see, P and Q then are is not forward derivable. It is a mistake to forward derive. I don't really have a good way of indicating that, but P then R. Okay, so if I have P and Q, then R, which is interderivable with not P and Q or R, which is interderivable with not P or not Q or R. Which, I don't know, there's no continuation there, so you can't and down. Like if I say, this is a system error. Maybe the trick here if we carried A as a subset of B, then we would have T as an element of A, maybe last note. Before I make a brief Wittgensteinian observation, if I say T is an element of A and something I don't care about, then T is an element of B. And A is a subset of B. So not T is an element of A, or not blue. Or T is an element of B. And A is a subset of B. And the solution to this might merely be saying that we already assume that A is not the empty set. Maybe, but okay, so if I distribute this through, no, it doesn't work, because it's saying not T is an element of A. Okay, but if I say not T is an element of A, and if T is an element of A, then T is an element of B. No, that's not useful either. Alright, I'm not sure how we're going to complete this proof. Alright, the Wittgensteinian point. What is it? Perspicuity. Perspicacious. Is the proof surveyable? In the literal sense, maybe. There it is. More or less. Yeah, well, a lot of that repeats. Well, so Wittgenstein's point is that proofs are about proving. The point of doing a proof is to prove something to someone. I present a proof to convince someone of something. So the proof here, I would say, is not of the original expression. That's not really what I'm trying... Well, what I'm trying to prove is the original expression and something in addition. Or what I'm trying to prove is something tangentially related to the truth of this assertion. Namely, that what I am interested in proving is specifically the derivability. Which is a distinction that maybe Wittgenstein wasn't in such a good position to make. If I can prove the derivability, then I can plug this into a computer and it will behave as expected. Any program that relies on the truth of this theorem would behave as anticipated, behave as if this is true. So the point is to show that, yeah, well, I mean, this is all meaningless to me. What this is proving is the derivability, which I mark by saying it's forward derivable. That's all I care about. I don't care about what this is telling me. I only care about the derivability. Anyway, that's it for me for now. See you soon.